Okay, we are go back to the problem we had for example when we started. When we left last time. Just a couple of announcements. I think all of you are here to hear about spring break next week, right? Okay. Just wanted to make sure you knew Jake would be here if we didn't tell him. Okay. No classes next week, Jake. Okay. Oh, get that. All right. Okay. And this is something, they sent it to me Monday. I picked it up in my box after this class was over with. There was a grand opening yesterday on the Birmingham East and West campus, but West campus was probably first. They built a brand new academic success center. It's finally completed. You can go view it. They will give you tours if you can find someone to do it. They were giving them yesterday. I haven't been in the building. I've been watching it as it's been being built. But yesterday was the ribbon cutting and official openings. And then also there's a new residence hall that's right, and this is on the East campus. The academic building's just barely on the West campus. It's on Wilson Road, which is a dividing line, but it's on the west side of Wilson Road. The new residence hall is right next to the old one, and it's not an old one, it's another fairly new hall, and it's on the East campus. Okay, so that was yesterday, and sorry you missed your refreshments. They had refreshments too. That would have got students there. Okay, but they were giving tours, guided tours, so you could probably still get someone to show you around. Get it in time to make the announcement Monday. Okay, that's all I can think of right now. Don't leave today without your third test, because Jake was really complaining if we weren't going to have calculus for a week. He wanted a test to work on. Okay, so got it. So we'll get that to you before this is over with. All right, any questions on anything we've done up till now? All right, we were working on this example. It's example 3 on page 237. This is chapter 3, application of differentiation. This is section 3.9, the last section in the chapter. That's why the test is for now. And we were working on example 3. We got started on it, but let's go back and just review quickly what we've done. Measured radius of a ball bearing is 0.7 inch. So that's the measured value. Okay. All right. As shown in the figure, the measurement is correct to within 1/100th of an inch. Okay. So technically, if you were doing this, you probably should have written this as 0.70 inches as your measurement if you're accurate, correct within 100th of an inch. But this is a math book, not a physics book. Estimate the propagated error in the volume of the ball bearing. Okay, and we determined last time after much hand-wringing or whatever was volume was equal to 4/3 pi r cubed. Okay, remember this is the radius here, 0.70 inches. Okay, and the tolerance, you might say here, that's more of an engineering word, is the R is the delta R is how they say it. I wrote it last time and it was okay, but I'm trying to do it more like they did. The delta R is, and do they use, yeah, they use less than or equal to minus 0.01. Ooh, that's ugly. Oh, let me clean that up a little bit. I wrote too close. Okay, barely read the delta R, but let's leave that alone. Minus 0.01 less than or equal to the error in radius that's less than or equal to 0.01. Okay, the way I wrote it before was r is between, I think I did anyway, I meant to, 0.069 and 0.071. Okay, that's the other way you could phrase that. All right, now, putting it in terms of, well, the other thing we did was take the derivative. I think we did this last time. Yeah, I remember it. Okay, dv dr. Okay, now in this case, not x's and y's, the volume is your dependent variable. It depends on the radius. Okay, so we're taking the derivative of v with respect to r, with respect to the independent variable r. So dv dr, anyone remember what it was? 4 pi r squared, which I remember commenting it's rather bizarre, the derivative of the, or it may not be that bizarre, but it's, well, that the volume is that happens also to be the area of the sphere. Okay, so here's Devin. All right. Okay, now, you might say, why did we take that? Well, because what we're dealing with is let's see, estimate the propagated error of the volume of the ball bearing. Well, the actual error would be your delta V. Okay, we're going to approximate that by our dV. Okay, now, if you take your derivative here and rewrite that in differential form, dV is equal to 4 pi r squared dr. Now, it looks an awful lot like you multiply both sides of the equation by dr, doesn't it? But a lot of mathematicians, and you were a mathematician, right? It's sort of, okay, it might make them call a wall to say that because that's an operator. It's not a fraction, okay? But in effect, that's what a differential does. And being more on the science side of things than the math side of things, that works for me, okay, to do that. So your dr, that is your plus or minus 0.01 inch. That's your dr, okay? Your r, of course, is your 0.07. I think it should be 0.70 inches. So we're going to approximate the dV by 4 pi times 0.7. I'll leave off that just to make it easier to write. Squared times plus or minus 0.01. Okay. So, did it just flick off and back on? Someone, yeah, you'll need your calculator. It's got a pi in it. 4 pi times 0.49 times 0.01. Anyone punched it in? 4 pi times 0.49 times 0.01. Okay, I think that's probably enough precision there, and that's would be in cubic inches. Okay, because the the 0.7 is in inches. You're squaring that. That'd be square inches, and the 0.01 is in inches, so that would be cubic inches. So your approximate error in your, how did they say it? Yeah, estimate the propagated error in the volume. That would be approximately 0.06. I'm going to leave it like that, cubic inches. Okay? Now, I hope that won't come as a shock to you that even though the radius was pretty small, this is 6 times as much. Still pretty small. It's 6 times as much because, like, they use the right word, propagated. The error grows, okay? And by the way, this is a plus or minus as well. because that was plus or minus up there. Okay. So it could be less or greater. It'll come back. Okay. And they put all sorts of digits out there. How they got that much precision when they only had one significant digit and all the other measurements, not too sure on that. But anyway, that's what they got. Now, all right, of about 0.06, and they finally say that. That's correct. Would you say that the propagated error in example 3 is large or small? The answer is best given in relative terms by computing. All right, here we got Frank. Okay, and this is what I started doing last time. The answer best given in relative terms by comparing, oh no, I'm sorry, not the delta V, the dV with the V itself. Okay, well, what was the volume up here if you put in just what you expect it to be? 4/3 pi times 0.7 cubed. What would that be? See, what they're getting at, this seems like a pretty small number. We can live with that, it's not too bad. But what do you get when you plug this in? What is the actual volume of that? 4/3 times pi times, I can't do that one in my head, 0.7 cubed.
1.437.
Okay, we'll let you ride with that. And that would be cubic inches. Okay? So we're going to compare this to that, and what you do is talk about the relative error, okay? And they didn't actually compute it, did they? Sorry. They did it by calculation, and that was dV divided by V, and we'll see if we got the same thing. And that would be 4 pi r squared dr divided by 4/3 pi r cubed. Okay? Well, you lose your pi's. That's sad, isn't it? You lose the 4's, and we lose 2 of the r's. Okay? So what we have left is 3 dr, because the 3 is on the bottom end of the denominator, so it flips over to the top, over r. Okay. Now, do that. 3 times plus or minus 0.01, that's your dr, divided by the 0.7. What does that give you? It'll come back. I have great confidence. Anyone get it? 3, that's pretty easy. 0.03 divided by 0.7. All right. The preachers come. Okay, good. .0429. Okay. Make that a percent, and that's about plus or minus 4%. Okay. Not bad. Okay. But much greater than if we took the original, do 0.01 divided by 0.7. Just to see what you get. 0.01 divided by 0.7. Your dr divided by your r. Okay, so that's about a little bit more than 1% error. So you jumped up to 4% error. Still not bad. Okay, plus or minus 1%, plus or minus 4%. Again, not bad, but you see how the error grows or propagates because you're multiplying your error you're cubing the thing that you're not too sure of, and that cube value that the error grows. Okay. All right. Any questions on that? Now, if we wanted to, we could take the time of doing this. Let's see. This is your it's pretty easy. It's right here. 0.06, and we've rounded this, I understand. Use this one. 0.0615 divided by 1.437. Just for funsy, we'll do that. 0.0615 divided by 1.437. Okay. See, it's very, very close to what we got there. That was easier doing it literally and not doing all the calculations. I just didn't even think about doing that. But you see, that gives you the same answer. We just had round off error. That propagated to this one, okay? You got 0.03, we got 0.043. Last time we got 0.029. You propagated some error by the round off error that you did. Probably in both of those. So errors grow, okay? You might think it's just a little mistake, but errors grow. All right, sorry, that was way too much. And they said 4.29%. They used way more digits. I think they were justified in using. Okay, any questions on that? Oh, I forgot. They show us this. The formula for the volume of a sphere is that. If we could just go one more slide, we would have got it, where r is the radius of the sphere. So you can write r equal 0.7, and that's what I was writing. Delta r is plus or minus 0.01. 0.01 is negative, is less than your change, and 0.01 is greater than or equal to your change. So that's your possible error. To approximate the propagated error, differentiate dv dr equal 4 pi r squared, and then write that your actual change of error is approximately your differential change of error. So rewrite the derivative as a differential, and that is, they didn't show you, but that's the 4 pi r squared dr. Okay, writing that as a differential. Okay. Plugging that in with, of course, the r being 0.7 and the dr, they called it delta r there, we're saying that's the same. The dr is 0.01, plus or minus 0.01. Plug that in and you get 0.06158 cubic inches. Where they get all those significant digits, I'm not sure. So the volume is propagated error about 0.06, they round it there, cubic inch. Okay? Now, the ratio of your error in volume to the actual volume, or the best guess of the actual volume, just do your literal equations there. 4 pi r squared dr divided by 4/3 pi r cubed. And those reduce, like we did, 3 dr over r, plugging in what those values are, dr being plus or minus 0.01 and 0.7 being your r. Your ratio there is a 0.0429. That's called the relative error. That's the relative error. The percent relative error is then moved into the decimal two places to right as normal. And that's 4.29% error, which doesn't sound as good as maybe 0.06 being the error. Okay. Now, enough of that. Probably too much of that. Let's calculate some differentials. I thought we were doing that. Okay? Each of the differentiation rules can be written in differential rules as well, a differential form as well. U and V, any two differentiable functions of x. The constant multiple rule, remember we did have dcu du would be c du, well, be c. Well, just multiply. Well, I didn't say that. Put on both sides the du. Write it in differential form. Sum of the difference. Actually, they are, sorry, let me back up. They are doing something a little different here. They're leaving out the dx period, okay? Because this should be, they're differential functions of x, so this should be d of cu dx is equal to c times du dx. They just got rid of the dx's altogether. Same thing here, derivative with respect to x of this sum of the difference of the differential of the sum of the difference of two differentiable functions is the sum of the difference of their differentials. And the product, the differential of the product of two functions is the first times the differential of the second plus the second times the differential of the first. Same as before in our good old favorite quotient rule. The differential of a quotient is low d high minus high d low over low low. Same as before. You just don't have to write all the dx's in there because they're not really doing anything but just telling you what the independent value is, the independent function is. So let's do a few. Oh man, they've done them for us, haven't they? Forget that. What's the derivative? dy dx. 2x. What's the differential form? Say again? 2x times dx. Yes, exactly. And here they put the dx in here. So I found it sort of bizarre how they wrote it on the previous slide, whereas in reality that's how we would write it with the independent variable on the right-hand side. Okay? This one, what would be the first thing you do before you take a derivative? Yes, in the exponential form, that would be y is equal to x to the 1/2. What would be the derivative of y then?
Be 1 over 2 times the square root of x.
All right, 1 over 2 times square root of x. Actually, I was reading my hand. Oh, no, never mind. How would you write that in differential form then? Not that bad.
Dx over 2 times square root of x.
Okay, yeah. dy is equal to dx over the same denominator. Okay, again, here they're using the differential as I was expecting them to on the previous one. Okay? All right. How about this one? What's the derivative? Two cosine x. Okay? And the differential?
2 cosine x times
dx. That's it. It's real hard stuff, isn't it? I wish I could figure out a way to make it harder, but I haven't managed to do so yet. How about that one? Anybody? dy dx. Help me.
Negative sine x.
Okay? I know there's a negative sine x in there somewhere. Anything with it?
X.
Yes. The negative x sine x, that's one part. Other part?
Cosine x.
Plus cosine x. Excellent. And then to do the differential, you just do this thing. I usually like to write the plus first, even though the rule doesn't say that. It just, to me, is easier. And then do the dx at the end. Just move the dx over there. Write it in differential form. So very, very similar. Okay? I think there's one more, isn't there? Yes. What would you do first on that?
The exponential form.
And what would it be?
X to the negative 1.
And then what would be the derivative of that?
Negative 1x to the negative 2.
Okay, or negative 1 over x squared. And then write it in differential form. Multiply by. Well, I didn't say that, did I? Okay. Move the dx over there. Write it in differential form. dy is equal to minus dx over x squared. Okay. Now, another reason we're doing these now, when you go to integrate, you don't see things in derivative forms as much as you see them in differential form. What we'll be doing is integrating both sides and set up for an integration. You're not there yet, but just let you know this isn't just something they said, oh, let's have something else for them to worry with. You know, there is a reason for it, okay? Not that you'd worry. Never mind, okay. All right, the notation in example 4 that we just did is called the Leibniz notation for the derivatives and differentials named after German mathematician Gottfried Wilhelm Leibniz, I think is how you pronounce it. Okay, by the way, he was the compatriot, you might say, contemporary, let me put it that way, contemporary of Newton. He's a bit younger than Newton. Newton was notorious for wanting to make sure he had everything perfectly worked out before he published or did other things. And to the extent that he quizzed others, and he would send some of his work and say, this is what I'm working on, what you think? Is this making sense? You know, is this, am I on the right track? How he phrased it, I'm not sure. But anyway, he did send some information to Leibniz, and Leibniz was more known for getting it out there as quickly as possible. And there, where the rub came, Leibniz published his calculus derivations before Newton did, okay? But Newton had plenty of documentation. He had been working on it for years before Leibniz published his. But Leibniz did use a very different notation. And that's probably the strongest argument. It wasn't plagiarism, but he could have just changed the notation. The sad news is these two brilliant minds spent most of the rest of their careers fighting over who discovered it first. You know, and I have a right, yeah. Why didn't they just, okay, bury the hatchet, let's keep on and do some more math, okay? Who knows where we'd be? Okay, all right. Differentials can be used to propagate function values. To do this, for the function given by y is equal to f of x. Okay. So, f of x plus delta x is approximately equal to f of x plus your differential in y. Okay? But, of course, the differential in y is f prime dx. Okay? Because dy dx is f prime dx. So, what it's saying here, if you move a little where on x, that's the same as starting at f of x and then moving up just that linear approximation that we were talking about before. As this is derived from the approximation that delta y is equal to f of x plus delta x minus f of x. Now, and that's approximately equal to dy. So, not completely clear how they say this is derived from there, but it's basically the same thing we did before. The key to using that formula is to choose a value for x that makes the calculations easier. Sounds like a winner for me, okay? So let's see what they mean by that. Here's example 7. Use differentials to approximate the square root of 16.5. What's that? Oh, wait, you're right. They skipped a bunch, didn't they? And I wasn't paying attention. So they were talking about notation 4, so I thought, so let's go back and do example 5. Very good catch there. Okay. All right. Y is equal to, okay. Y is equal to f of x, sounds like a good thing, is equal to sine 3x. Okay? And what it says is find the differential of that form. Anyone want to hazard a guess? Not that bad. I'll get it started. dy is equal to If you want to go all the way back and make it a derivative and then change it to a differential, that's fine. But yeah, it's not too bad just doing it this way. What you get? Anybody? Cosine of 3x, perfect. Times what? Well, dx will certainly be there, but you have a chain rule. Times 3. Perfect. There it is. dy is equal to 3 cosine dx. I'm sorry. 3. dy is equal to 3 cosine 3x dx. 3x dx. I'm getting my tongue wrapped around my eye tooth. Okay. Can't see what I'm saying. All right. Let's do example 6. Y is equal to alpha of x. I'm so glad they put the alpha of x in there. That really helps the problem a lot. Which is equal to x squared plus 1 to the 1/2 power. I'm glad they wrote it in that form already, so we didn't have to do anything else. Now they actually go through the f prime stage. Okay? If you need to, do it. But it seems like to me it's just as easy to just go right to dy is equal to what? Take all the steps you need. 1/2. That sounds like a good beginning. X squared plus 1 to the negative 1/2 times 2x. Good chain rule catch there. dx. Perfect. 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 Okay. Now, to clean it up a little bit, dy is equal to, the 2's can go out. They've been dating. Never mind. Okay. And that would leave us simply x over x squared plus 1. You could even write that square root of x squared plus 1 dx. Or any way you want to. You don't have to go back to radical notation. They didn't start in radical notation. And they left it in exponential. So you could leave it just like that. dy is equal to x squared, or x times. The only problem with that is it looks like they're multiplied and they're not. X times x squared plus 1 to the minus 1/2. That's a little clearer exactly what's going on there. Let's see how they leave it. Hey, amazingly, they do it the same way I did. Something must be sick in their minds. Okay. So, got it? There are our 2 missing examples, 5 and 6. So let's move on to example 7, because we've already done the interlude there. We did that part. Let's do example 7. Use differentials to approximate that. Now, what function might we be dealing with here? What is the function operating on that number? The what? The square root of x, exactly. Which I immediately want to write as something else. Different form, same thing. X to the 1/2. Okay? And then what might we want to do? Yes. Let's just call that our y and then say dy is equal to, and what would that be? Help me?
1/2.
1/2. X to the minus 1/2. dx. Perfect. All right. Now, that's your differential form. And basically, we're looking for the y, okay? And if you look up above, I'll write it down again because it's lost it here. The f of x plus some small delta x is approximately f of x plus your differential, okay, which is your alpha prime of x dx, which is exactly what this is. In other words, your dy, okay? Make sense? Okay. So we're looking for the square root, that would be our f of x, okay? The f of, now what would you guess the x might be? The x. Keep it simple. The 16.5 is going to be our x plus delta x.
16.
Ha! Let's let the x be the 16 plus the delta x is 0.5. See what we've done there? Now, what is your F function? Square root of x, and that will be square root of, if your x is equal to 16, all right, this will be 4 plus, and then we'll plug in this. 1/2 of, let me go on and write it, 1 over the square root of 16. That's your x. It's not anything else. That's the x. And then we'll have our delta x. And what's our delta x? If this is the 16, the delta x is your dx is delta x. What is that? 0.5. So that would be, I can't write, 0.5. All right. Ugly as this looks, it would be 4 plus, and what's the square root of 16? We already done it once? 4. So this would be 1 over 8 times 0.5. That would be another half, wouldn't it? So that would be 4 plus 1 over 16, which would be, let's see, 4.0125. Is that 1/16? It doesn't seem right. Yeah, wait. Okay. A quarter would be 0.25, an eighth would be 0.125, 0.065. Okay, sorry. I went too far. Is that better? Is that right? That seems better. All right. I'm not too sure of it, but I think it may be the case. Let's see. Check in the book and see what they got. Yes. Okay. Now, let's compare that with the square root of 16.5. This is our approximation using differentials. What is the actual value? Square root of 16.5. 4.062. Is that what you said? That's what the book said too. So, not too bad, okay, for government work, right? All right. And of course, with a calculator, what difference does it make? Just plug in and do the square root. But this shows that you can approximate these things with the differentials. All right. Kind of moot points, aren't they? Oh, let's see how they did it. I bet you they threw a few more chinks into it, but let's see if it makes sense. Okay? So, we'll use the function f of x equals square root of x. Good choice there. And then your f of x plus delta x would be what we had before, approximately f of x plus your f prime of x dx. Okay? Well, we had already done the derivative, or this is a differential, and so you see it's basically y plus dy, okay, or delta, or dy actually. And to me that's a lot easier than doing all this, but it's the same thing. So that'd be square root of x plus 1 over 2 times the square root of x dx. And that's going to be approximately what this is. If you wisely choose x equals 16 and your delta x equals 0.5, then just plug it in. And that would be okay. Here they actually did the thing on this side, and on this side here's your approximation. Square root of 16 plus 1 over 2 times square root of 16 times your 0.5 is your delta x, and that gave you 4 plus 1/8 times 1/2. So where have I seen that before? Okay. And that would be 4.0625. And on the right-hand side, the actual value is that's approximately 4.0625. That's what we just calculated. The approximate value. The true value, boy, as if that wasn't clear enough, here's something to muck up the waters, okay? The tangent line to the approximation is this, and for x values near 16, the graphs of f and g are close together, as shown here, okay? So it's 16.5 would be just a little bit further there, and let's see what it's, well, okay, and then they end it right there, okay. That sounds like a good place to stop, doesn't it? Okay. They don't do any calculations with it, but that's why. But you notice here the tangent line is always above the curve here, and that's why we came out a little bit greater, 4.0625 rather than 4.0620. Not far off at all. You see the blues just showing through up there. That's way up here around 20, so 16.5, not far off at all. Okay. And I'm sure there's a reason why we needed to put the tangent line in there, but it's all right. It's there. All right. That, I think, then, does finish 3.9. And again, odd numbers or answers in the back. Tutorial help to work out solutions or at Calc Chat, and then further illustration is given at calcview.com. So, and these are perfectly free websites. You can go to it. You don't have to have a code or anything else. Anyone can go to it. My wife can go to it, and why would she? But she could. Okay, anyone could. So do any of the odds 5 through 9. They're all at Calc Chat. 7's at Calc View. Do number 11, it's a Calc Chat. Do any of the odds 13 to 17, they're all at Calc Chat. 13's a Calc View. Any of the odds 19 to 27, they're all at Calc Chat. 23's a Calc View. Do 29, it's a Calc Chat. 31's a Calc Chat. There's an area problem, 33 should be at Calc Chat. A volume problem, 35 is, and surface area at Calc Chat. Stopping distances at 37, pendulum at 39. You don't have to do all these, but any of these that float your boat, grab your attention. A projectile motion at 41, and then do any of the odds, either 43 or 45. They're both at Calc Chat. 43 is at Calc View. You can explore doing 47. I assume this will be at Calc Chat as well. A couple of true false, 3 of them in fact, 49 to 53. Do any of those you would like. They should be at Calc Chat as well. That does finish 3.9. If you need some more practice, and I know you do want to do that, just whether you need it or not, these are also at Calc Chat. None of these are at Calc View, but any of the odds 1 through 7 are at Calc Chat. 9 or 11 are at Calc Chat. Any of the odds 13 to 17 are at Calc Chat. Mean value theorem 19's at Calc Chat. Any of the odds 23 to 25 are at Calc Chat. This goes back to the first part of the chapter. 27 to 33 are at Calc Chat. 35 is at Calc Chat. Any of the odds 37 to 41 are at Calc Chat. Second derivative test 43. Any of the odds 43 to 47 at Calc Chat. You can think about doing 49 if you'd like. 51s are writing things, so that might give you an idea of where to go on a research paper maybe, or not, whatever. There's modeling data, 53 should be at Calc Chat. Any of the odds 55 to 63 should be at Calc Chat. Horizontal asymptotes 65 or 67 should be at Calc Chat, and 69 through 77 should be at Calc Chat. Then there's a bunch of exercises, more word type problems. Any of the odds 79 through 87 should be at Calc Chat. Newton's method is 89 or 91. They're at Calc Chat. Oh. Some of those from those word problems, I think, is the optimization section that we skipped. So if something looks unfamiliar, skip it, because we probably didn't do it. 89 or 91 should be at Calc Chat. 93 should be at Calc Chat. 95 should be at Calc Chat. 97 should be at Calc Chat. 99, and then finally 101. And then they have a little blurb on problem solving. You can certainly read that if you'd like, and we're ready to start an integration. But before we go there, let me give you, if I can find it, your test. Okay? Had them run off. Let me see if I can find it. And by the way, folks, since we have a little interlude here, and we also have a new student here, okay? Be sure to remind me to get you marked. Here we go. Test 3. This is a Chapter 9 test, and like I've been referring, it covers all the sections, I think, except 3.8 or 3.7. We snuck in too. Okay. Glad I handed out your test. So missed that. Okay. Pass 1 back. You'll pass 2 back. Get D1. Okay. Let me make sure I get everyone marked here. I think you can figure out, let me see if I can go back and say it quickly, or at least approximate it quickly. 3 was a long chapter, wasn't it? Goodness gracious. Okay, not too far. All right. I'm pretty sure that 1 and 2 came out of 3.1. 3 and 4 came out of 3.2. Five and 6 pretty much, I think, came out of 3.3. 7 came out of 3.4. I think we skipped 3.5, so you don't have any of those. 8 came out of 3.6. We skipped 3.7, and then 9 came out of 3.8, and 10 came out of 3.9. Okay. I'm sure y'all could have found that out yourselves, but since knew you would be partying on spring break, I thought I'd save you some of the effort. Okay. Now, let me get Taylor here and Ayana here. Ayana. I had it right the first time and blew it. Okay, never mind. Okay. All right, so that means we're only missing Cedric, he hasn't come in yet, and Taylor, and Elise. Okay, so 3. Second. Oh, Taylor's here. Elise. I got off of Josh. That's the one. I got off of Josh is missing. So Cedric's missing, Josh is missing, and Elise. Okay, good deal. And I think I just lost my place as I went back to do that. Okay. All right. Let's get out of this then. How are we doing time-wise? I haven't even taken my watch out of my pocket yet. I at least brought it today anyway. Okay. We go until
15 minutes.
Yeah, we got 50 minutes. Excellent. All right. We'll discard that and get out of that and go to 4.1. My stomach's saying it's lunchtime, and he's totally wrong. Okay. Okay, we'll go from current slide. All right. So, chapter 4, we're moving in integration. I told you the differentials were moving us right that way. So 4.1, we'll look at antiderivatives and indefinite integration. Okay? The second big part of calculus. Differentiation, the first part, integration or antiderivatives, the second part. And just as a little background, let's talk about these. Objectives here, write the general solution for the differential equation. While we're jumping in differential equation, not too sure, and use indefinite integration, integral notation for antiderivatives. We'll use basic integration rules to find antiderivatives and find a particular solution of a differential equation. Why are we in differential equations? That's the next course. I mean, that's several courses off. That's 126, 227, then usually differential equation. But we'll hit simple ones. Basically, the concept here, just like you've always done in math, right? Way back, if you can remember this far, you learned to add, right? And once you finally got all those flashcards straightened out in your mind and stuff, and you thought, hey, I've got math conquered now, then they turned around and had you subtract. Which did what? The inverse operation of addition. It undid addition. So, finally got that figured out, and then, I'm almost through with math now, right? No, here comes multiplication. And once you finally got all those flashcards, they all didn't use flashcards, but way back in the day, that they used to use those. I've never used them either. But anyway, so you finally got the multiplication down, and then what did they do? Had you undo multiplication with division. And then usually much later, they came up with this idea of let's raise things to powers. Okay, that makes repeated multiplication of the same number much easier is raising it to a power. And then about the time you got that figured out, what did they do? Had you take roots, which undid powers, right? Okay? And then much later we do things like coming up with new functions like exponentials, and then you do the logarithms. Or you did logarithm, then you did exponential. One way or another, you undid what you just did. And when you did sine and cosine functions in trig, you did inverse sines and cosine functions in trig to undo that. And back in pre-calculus algebra, you also did functions and their inverses. So you've always been doing inverses. Well, now we're stepping it up a notch. Those were operations and then functions. Now we're doing a whole process. What we were differentiating, which is something you do to functions, now you're undoing that, doing antiderivatives, okay? And that's the whole deal of integration. Except they stand completely independent of each other, just like multiplication and division do, you know, but they are related. So we'll start with antiderivatives. It's sort of like antimatter, only different, okay? So, to find a function, capital F, since when you take a derivative, you're going to use little f, let's do an antiderivative will be a capital F then, okay? Whose derivative is f of x equal 3x squared. I bet you can come up with a capital F that this would be the derivative of it. What would that be? Took the derivative of some function, capital F, and you came up with 3x squared. Where did you start? X cubed, of course you did, okay? You might use your knowledge of derivatives to conclude that the capital F must be x cubed because the derivative of x cubed is 3x squared. Ha! That was your little f here, so your capital F had to be that. The function capital F is called the antiderivative of little f. So here's the definition. A function, capital F, is the antiderivative of a little f on some interval I when capital F prime is equal to little f. Okay? For all the x's on that interval I. Okay? Pretty straightforward definition. So basically, what we're going to be doing for a while now is undoing what we just did, taking antiderivatives. Okay? So your Jesus answer may not work anymore. Okay, so let's go from here. Notice that capital F is called the antiderivative of F rather than the antiderivative. Okay. Capital F is called an antiderivative of F rather than the antiderivative of F. Okay? And here's why. You said x cubed gave you 3x squared when you took a derivative. What if you had x cubed minus 5? What would be the derivative of that? 3x squared again. And x cubed minus, plus 97. 3x squared. Plus 97,485,000. It doesn't matter what you put there. You still, the derivative of all three of those functions is exactly 3x squared. So therefore, it's not the antiderivative, it's an antiderivative of F because there's a bunch more. They're all antiderivatives of F. Now, what's the difference in all these? A constant. Just a constant. No other x's in there. If there was an x in there, then that would mess it up. But if it's a constant, it's fine. So in fact, for any constant c, the function f of x equals x cubed plus c is an antiderivative of f. Okay? Because any constant in there will take a derivative of this and you get 3x squared plus 0. Okay? 3x squared. So representation of antiderivatives, if f is an antiderivative of little f, capital F antiderivative of little f, on some interval I, then g is an antiderivative of f on the interval I, if and only if g is of the form capital G of f is equal to, of x is equal to capital F of x plus c, for all x's in I, where c is a constant. I found it really useful. They interjected another function name in there, g, but it's fine. What they said is true. So, when you're doing antiderivatives, you're not through until you put the plus c on it in some sort of a form. Okay? Now, using that theorem we just showed, you can represent the entire family of antiderivatives of a function by adding a constant to a known derivative. For example, knowing that another way to write a derivative, remember, capital D sub x, that's being the derivative with respect to x of x squared, what would that equal? 2x, okay, yeah. You can represent the family of all antiderivatives of f of x equal 2x by g of x is equal to, they're coming back to g, x squared plus c. Because when you take the derivative of this, you're always going to get 2x. No matter what the c is, it'll always be 2x. Where c is any arbitrary constant. Positive, negative, fractions, decimal, zero, rational, irrational, just has to be a real number. Okay? Not going to deal with any complex numbers at this point. The constant c is called the constant of integration. Okay? And you'll run into these a lot in physics, and they can have some pretty important meanings there. And in differential equations and everything else. A family of functions represented by capital G is the general antiderivative of f, and g of x equal x squared plus c is the general solution for this differential equation. So now they're calling it a differential equation. G prime of x equal 2x. You undo that by taking the antiderivative of it, or thinking of that. The differential equation x and y is an equation that involves x, y, and derivatives of y. Okay? For instance, y prime equal 3x and y prime equal x squared plus 1 are examples of differential equations. Okay? Now, both of these examples only show derivative of y and some functions of x, okay, involving x. You don't see the other y in here, but they can be. They just didn't give you any with that. So now, example 1. Find the general solution for this differential equation. dy dx is equal to 2. So what's your process?
Just be 2x.
Okay. Y would then be equal to 2x plus c. Excellent. Now they right now are using capital C's all the time, which is fine. I don't even want to waste the ionization to make a capital C. I'm going to put a small c's most of the time. Who cares? It's just some constant. Okay? But that's exactly what you do. What is it? The function whose derivative is 2, that would be 2x, or any constant, anything added to 2x, constant added to 2x. So let's see what they do. Oh, to begin, you need to find a function whose derivative is 2. Oh, let's see, what would that be? One such function is y is equal to 2x, and then now you use theorem 4 to conclude the general solution. Yeah, I went through all this in my brain, is y is equal to 2x plus c. Capital C, by the way. Okay, it doesn't matter. Now, they show some of these functions, graphs of some of these functions. Here is when c is equal to 0, you're here. When c is equal to -1, you're over. Oh, yeah, -1, you're here. +2, you're here. Those are the y-intercepts, by the way. So it's a linear function. And sure enough, all those have a slope of 2. And that's what we were told. dy dx is equal to 2. Every line that has a slope of 2 is and they just differ by a constant. Okay. Any questions? Seems like we're beating dead horses here, but let's go. When solving a differential equation of this form, okay, dy dx is some f of x, what we do is often convenient to write it in the equivalent differential form. dy is equal to f of x dx. Now, jumping way ahead to do this, but this is exactly what we do when we're doing integration. And they do mention it here. The operation of finding all solutions of this equation is called anti-differentiation, which is a very long word with lots of syllables, or finding the indefinite integration, which is just about as many syllables. Okay. It's denoted by the integral sign, that little s there. And actually, it really does come from, sort of from an s, okay, in a strange way. All right, now, sort of surprising they jumped this far this quickly, but it's perfectly right. I was wanting to do it earlier, but I'm surprised they did it now. Okay. They haven't shown you how. I guess the next slide will. Yeah, here's what they do. I'm going to do it this way. I would integrate both sides. Okay. That's how I think of doing it. Now, this is jumping way ahead because, like I mentioned before, an integration undoes a differentiation. That's why they call it antiderivative. Okay? So basically, the integration undoes the differential here, and that leaves you just the y. So that's kind of how I think of it. Okay? Now, so that's why they say on the next slide, y is equal to the integral of f of x dx. Now, you can't just undo the dx here because you got the f of x with it. So you have to undo this function to do that part. And that's why it's indefinite integration. Okay. So, the y is the dependent variable. The variable of integration is whatever follows the d here, the x, okay, in this case. If this depends on x, this function depends on x, that's why you can't go on and do this. You have to include that in it. This is called the integrand, the f of x, okay? The antiderivative of the f of x, dx actually, is your capital F of x. And then the constant of integration is your plus c, okay? So that's basically your process here. What's the antiderivative of this function, and then add a c to it. Just like we were doing before, now we just introduce a symbol that tells you that's what you're doing. The expression integral of f of x dx is read as the antiderivative of f with respect to x. And I've mistakenly been called the integral of f of x dx. That is also what it's called. So the differential dx serves to identify x as the variable of integration. The term indefinite integral is a synonym for antiderivative. So when we're doing integration, I'm going to say, what's the antiderivative, okay? Even when it's a definite integral, which we haven't even gotten to yet, I'll still say, what's the antiderivative of f, but then we'll just leave off the plus c, but we'll get there later, okay? That's coming up. So, I haven't been turning my pages. I hope I haven't missed any examples. We did that one. No, that was it. So let's look at some basic integration rules. Okay? The inverse nature of integration and differentiation can be verified by substituting f prime of x in for f of x and the indefinite integration definition to obtain the integral or indefinite integration of or antiderivative of capital F prime of x dx is just f of x plus c. Always have to have that. Now, why is that? Well, remember I said differentiation undoes integration and integration undoes differentiation within a constant. Now, I should have been saying that all along. Within a constant, it does. Well, this is a perfect derivative here, so just do the antiderivative of this and you get that. In other words, the integral undoes the differentiation. You're left with f of x within a constant, plus c. The integration is the inverse, and it's sort of like an inverse operation of differentiation, not an inverse function, inverse operation. So I use that for addition, subtraction, so. Moreover, if the antiderivative, indefinite integral, whatever you want to call it, of f of x dx is equal to capital F of x plus c, then, getting right to this, and it's lambda dx. Okay, if you take the derivative of an integral, you undo it, and you're left with what's on the inside. However, if you take the integral of the derivative, you undo it, but you're within a constant. So this one, when you do it this way, it's not exactly symmetric, because here you have to add the constant. When you take a derivative of this, it wipes out any constant. Because take a derivative of a constant, gives you 0. Okay, so, but antiderivative of a function, you have to throw in the constant to be completely general about it. Okay. So differentiation is the inverse of integration. Integration is the inverse of differentiation within a constant. Differentiation of integration gets you just what's on the inside. All right. Make sense? Kinda? Okay. So those two equations allow you to obtain integration formulas directly from the differentiation formulas as shown here. The derivative of a constant, of course, is 0. So if you are integrating nothing, you still could have a constant. That seems bizarre, but it's true. The derivative of k times x, of course, is anybody? K. Okay, K. Okay. So the antiderivative of k dx would be kx plus some constant. You always have to put a constant in there. Okay? Now, when you lose the integration sign anyway. All right. These next two don't quite fit. No, yeah, they do. Okay. Derivative of k times the function is what? The derivative of k times the function is, you just pull the k on the outside, and it's k times the derivative of the function. dy dx, d by dx of f of x is f prime of x. I mean, that's just pull the k on the outside. So if you're doing an integral, write that in differential forms and then integrate it, again, all you do is pull the k on the outside and then integrate the function as necessary. Notice we haven't done the integration here, so you don't have to introduce a constant. Only when you lose the integration sign do you introduce a constant. Okay? This one, the derivative of the sum or difference of two differentiable functions is the sum or difference of their derivatives. So when you're doing the antiderivative or integrating any two functions, okay, then it's the antiderivative of this one plus or minus the antiderivative of that. Or the integral of a sum or difference of two integrable functions is the sum or the difference of their integrations. Okay. Now this was our good old power rule. Remember it? How did that go? d by dx of x to the n. Derivative of x to the n. N to n minus 1. So if you're doing the reverse of that, if you're integrating in this, okay, what did you do here? You multiply by the n and reduce that by 1. Here, when you're integrating, you increase that by 1 and divide by that n plus 1. So you see, both functions are reversed. It's just that you have to remember what to do by it. Here you use the n to multiply, reduce. Here you increase the n by 1 rather than decreasing by 1. Then you divide by it. Okay. Divide by the new n, you might say, the n plus 1. You might say, but wait a minute, that would be hard to remember. No, not really. Because how would you take a derivative of this? N plus 1 times this. You need that n plus 1 down there to divide it out. X to the n plus 1 minus 1, which would be x to the n. And that's exactly what you got in there. So always, when you're doing an antiderivative, all you have to do is take the derivative of your answer and see if you get what the integrand was. It's a really easy check. But because you are using an integral sign here and losing it here, you have to add the plus 2. Oh, and what do we also note? This doesn't work when n is equal to minus 1, does it? Why not? Second, you have a 0 in the denominator, you can't have it. So that's going to require a special function. Hang on, we'll get there later. Okay? Maybe not this term, but later. Okay. Any questions on this? Just put your hat on backwards and just think reverse. Turn it around. No, I'm just kidding. Okay. Just do everything. Oh, here's a few more. Okay, what's the derivative of sine? Cosine. So what's the antiderivative of cosine? Sine plus c. Okay, don't forget your plus c. Derivative of cosine? Negative sine. So the antiderivative of sine would be negative cosine plus c. Of course. All right. Just when I was getting the signs right, now you go and do a derivatives that reverse them, right? Well, again, just think, what if happens when I take the derivative of this? I'll get negative, that's a positive, yeah. So yeah, that works. Okay, what's the antiderivative of, what is the derivative of tangent x? Anyone remember that one? Oh my goodness, no.
Secant squared.
Secant squared, perfect. So the integral of secant squared would then be tangent x plus c, of course. Derivative of secant x, oh, that was another fun one. What was that? Anyone remember? Strange, but true. Derivative of secant. Nope. Secant tangent, very good. So when you're integrating a secant tangent, which you do all the time, right? That would give you secant plus c. Okay. And then cotangent is just like tangent, only it's minus cosecant. Again, just a little memory device here for me anyway. When you're doing the functions, sine, tangent, and secant, those are positive. When you're doing their cofunctions, the derivatives are negative, which of course will be completely backwards when you're integrating. So derivative of cotangent is just like derivative of tangent, only it's different, okay? Minus cosecant squared. So the antiderivative of cosecant squared would be negative cotangent plus c. Perfect. And cosecant, derivative of cosecant would be so minus sign. What value? Cosecant cotangent minus cosecant cotangent. So if you're integrating, ever doing a cosecant cotangent, which I do all the time, that would be a minus cosecant x plus c. All right, good deal. Now, one thing, just to give you a little information here, I've decided I don't like about this book. I like the author. I like so many of the aids that he does. But this is just calculus, which sounds great. But he has another text, and we're going to it next year. But if you're still here next year, we'll still be using this book for the upper level courses. But only for the 125, we're going to go with, what is it called? With elementary functions or something like that. Notice what we haven't done is logs and exponents. So they wait and do a separate chapter and then have to redo all this with logs and exponents. So what we'll do, I'm going to go to the other text, which is already going to have brought in those for doing differentiation, and we'd be doing integration with them now. Now we have to fill them in separately in a separate chapter, which is a really awkward way to do it. So I found that out a while back, and that he did have another book with it. No, transcendental function, that's what we call it, not elementary function, transcendental function. Okay, so, what would you, oh, this is example 2. I hate they did it for you. How would you start that? Antiderivative of 3x. Yeah, integral of 3x dx. Pull the 3 on the outside. That'll be the 3 times the antiderivative of x dx. And what would that be? Oh, they don't show that. Okay, I don't have to hold my arm up there anymore. What would that be? Oh, what? Forget you saw that. Let's work it out. What would it be here? 3. What's the antiderivative of x? I might even write that as x to the 1, mightn't I? With maybe even a 1x to the 1, if that's helpful, which it really isn't. But say that one more time. Okay, right. Okay. You increase the exponent by 1 and then divide by that very increase. That's exactly right. What else?
Plus c.
Plus c. Okay. Now, here comes a place where things get a little silly sometimes, but they're okay. So this could be 3/2 x squared, and you could call it plus 3c. But guess what 3c is? If c is a constant? 3c is a constant. So why have that with it? In my mind, this is 3/2 x squared plus c. Okay. Forget the other. So a constant is a constant. Okay. So 3 times a constant is still a constant. So back it up and make it simpler with just the constant. Okay. That's how I would approach it. Let's see how they do. They may do it a lot differently, but I can't imagine how much. So that would be, oh my goodness, I must be sick in the head if I'm thinking like they do now. Okay, put the 1 up there and then use the power rule, and that'd be, and they wait until they do the integration, then put the plus c. I like it, okay? And that would be 3/2 x squared plus c. Yeah. So don't worry about doing the plus c too soon. Just wait till the end of the problem and add your plus c in there. Okay? The antiderivative of 3x, or the form of that where c is any constant. Okay. It's funny to see them say the antiderivatives, and that's actually true because with plus c you can have infinite number of them, in fact. Does that make sense? That was example 2. Okay? Notice in example 2, note that the general pattern for the integration is similar to that of differentiation. You take the original integration, rewrite it if you need to make it make more sense, integrate it, and then simplify it. Okay? And that combining the concepts together is just another way of simplifying, in my mind anyway. So, I think they're skipping goodness gracious, they're skipping a lot. So let's go back and pick up example 3. All right. What's the antiderivative of 1 over x cubed dx? What would be your first step? Any ideas? Second? Rewrite. The antiderivative, how would you rewrite that? X to the what?
Is that an x cube up there?
Yeah, that's an x cubed.
Okay. X to the minus 3.
X to the minus 3 dx. Okay, good choice. And now I think we can do our antiderivative. What would be the process of that? I know it's going to be an x. Okay, I got that part right. Okay, what next? What you do with your exponent? Add 1 to it. And what's negative 3 plus 1? Negative 2. And what you do with that negative 2 then once you've done that? Divide it by it. So I'm going to put the 2 down here but put the minus out there. Is that okay? And then what do you do? One last little step, you can't forget that, plus c. That should be it. Okay? Now, if you want to rewrite it, you can write it as minus 1 over 2x squared. If you prefer writing it that way, plus c, that's fine. However you want to do it. How did they leave it in the book? Negative 1 over 2x squared plus c. Good for them. Okay? Let's try to get this next one on it. The antiderivative of the square root of x dx. What would you do first? As dx. Okay, that's the exponent there, by the way. Now, what would that be? Three halves, add 1 to 1/2, you get 3 halves. And then what you do with that 3 halves? Yeah, divide by it, but I'm really lazy. I don't like putting a denominator in the denominator, so I'm going to invert and multiply in the same step and write it as 2/3. Now, if that doesn't make sense to you, go on and divide it and then work it out. But that, to me, is the easy way to do it. Dividing by 3 halves is the same as multiplying by 2/3. Right? That's how you do it. Okay? But we're not through. Oh, yeah, we are through, aren't we? Except for one thing. Plus c. Perfect. And how did they leave it? Well, they rewrote it. And this is really no simpler. That is perfectly fine. They wrote it as 2/3 x to the 3 halves plus c. Now, they didn't go back and write it as a radical again, which I'm thankful for. You could. In fact, let me ask you that. How would you rewrite that radical? There are 2 ways to do it. Now, as a radical, I'm sorry. Rewrite that exponential expression as a radical.
x per x raised cube.
Okay. You can either cube it there, or you can cube it there. Either one of those is exactly the same. And that's why I'm not going to go back and rewrite it that way, because you have two choices. Actually, I like that one a little bit better, but in reality, I do it that way. Okay. So leave it in exponential notation. It makes everything a lot simpler. And I'm all for simple, because I have a simple mind. Never mind. Okay. How about this one? The integral or antiderivative of 2 sine x dx. You can take as many steps as you need to make sure you know what you're doing.
Put the 2 on the outside.
Okay, I like that idea. And then do the integral of sine x dx. And I don't like to say what's the integral. I say, what's the antiderivative of sine x?
Oh, no, negative cosine.
Yes, minus cosine x. Almost done. Almost done. Plus c. All right. Little c, big C, I don't care. I've been writing big C just because they do. All right. Remember, if you're ever in doubt, just take the derivative of this thing. What's the derivative of minus 2 cosine x? Well, it's minus 2 times the derivative of cosine x, which is derivative of cosine x is minus sine x. So the minus takes out the minus, and sure enough, that's what you wind up with, 2 sine x. Okay. Because the derivative of c is 0. All right, so that was example 3. By the way, example 3 is, you can find at larsoncalculus.com, interactive version of that type of an example. All right. So let's move on to example 4. Okay? Integral of dx, what's that equal to? Anybody?
C.
Say again?
C.
Oh, just x plus c.
X plus c. Okay? Think of it this way. This is an integral of a differential, right? So the integral undoes the d, and you're left with just the x. Okay? And then you add the c to it, because it's an indefinite integral. Okay? Or you could think of it the way the book did, as the integral of 1 dx. Okay? And say, well, what is 1? Now, they didn't do this. I'm going to do this one. 1 is x to the 0th power. Are you in agreement or not? Yes, dx. So what do you do? Increase your exponent by 1. 0 plus 1 is 1. Divide by that 1 I just did. Okay, you saw that, right? And then add your c. Easier to me to think of this as this is the derivative of x, that's the integral of that, the derivative of x, that just gives you your x. Okay. All right, how we doing? Still got a few minutes, right? Yes. Okay, good. All right, let me clear the screen, because the next one may take a little bit more. I don't know, it may not. Okay. It's the integral antiderivative of x plus 2 dx. Okay. Now there's a couple ways you can proceed here. How would you like to proceed? You tell me. What do you see in that?
Sum difference.
Second?
You do sum.
It's a sum. It's an integral of a sum, so you can say that's the sum of the integrals. So that would be x dx plus integral of 2 dx. You don't have to do that unless it makes more sense to you, then by all means do it. So let's do that one first, the first one. What would you do with it? Okay, he's already right on top of it. Make that 2 and divide by 2. Okay? Now, here, please, wait till the end to add your c's, because it was only one integral to begin with. Don't do a c for each one. Then you'll think, was this 2c or is it, yeah. No, just wait and do it at the very end. Okay? Next. Plus 2x. Went right for it. You can move the 2 out here if you want to, or that's just 2x. Okay? And then what? Plus c. Okay, you need that. Now, if you want to clean that up a little bit, you could do it 1/2 x squared plus 2x plus c. That's fine. There's lots of different ways you can write that. That is just as good as that. There's no preference. Okay? In fact, they left it the first way. All right. Oh, and they did a plus c for each one and then said, forget it. Don't usually do it. Just wait till the end and add 1c. Okay. So let's do we have time? Yes. Okay. Let's do C. That's yes in Spanish. All right. Whoa. Antiderivative of 3x to the 4th minus 5x squared. Boy, did they jump a rabbit here or what? Okay. Plus x dx. Okay. Now, a couple ways you could proceed. How would you suggest? So you see it and understand it the best. Second, take the integrals of each term. Okay, yeah. That's perfectly fine. After a while, I think you'll find yourself skipping this stuff, but it's okay. Now, I'm being really lazy about it. I'm going to go on and pull the constants out at the same time. So that'll be 3 times the antiderivative of x to the 4th. Is that okay with you? dx. Minus 5. I'm going to pull the minus out there. The integral of x dx. Okay, my screen is collapsing on me. Plus the integral, oh, that was x squared. Oh, sorry about that. Plus the integral of x dx. Okay. Legal in most states. Okay. So what would the first one be? You see that that's an okay thing to do, okay, right? I just did 2 steps at once. First one, I separated each of these into integrals, and then since this is just a constant, I pulled it on the outside, minus 5 the constant, pull that on the outside, just leaving that x's inside. So that gives me a what? 3 5 over 5. Just like you did when you were differentiating, you just took the coefficient, put it out front, and to reduce by 1. This time, increase it by 1 and put it in the denominator. Whereas before you multiplied, here you divide. Before you decreased, here you increase. Okay, so that's what you got for the first term. Don't mess with the plus c's till the end. And what you have next? Minus 5 over what? 3 plus x squared over 2 plus c. Put it all at the end. Now, if you want to clean it up some, you can. And anyway, it's fine. You could say this is 3/5 x to the 5th minus 5/3 x cubed plus x squared, 1/2 x squared plus c. If you want to do it that way, you can. You can write it 3x5 over 5. 3x to the 5th over 5. There's lots of ways you can do it. If you are in doubt, just take a derivative of it. Derivative of this is 3 times 1/5. 5 times 1/5 would be 1, so it would be 3x to the 4th. D minus 5x squared. D plus x plus, and derivative of that is 0. So there you have your anagram. Really easy to check. Just take the derivative of your answer. Okay? And see if you get your anagram. and they wrote it in a fractional form like this. Any questions? Okay. All right. Think we can squeeze in one more before spring break? What you think? Okay, let's try it. All right. That's so sad. I won't see y'all for a whole week. How will I manage, huh? 4 minutes, okay. Let's see if we can do this. The integral of x plus 1 over the square root of x dx. Okay, now wait a minute. Back on those differentiation rules, or integration rules, I don't remember seeing how to undo a quotient rule. Oh, shucks. Oh, let's do that. Why not? What would that give you? The integral of? Okay. It's x over x, the square root of x, right? Plus, and that's a dx, plus 1 over the integral of 1 over the square root of x dx. Is that legal? What you're doing is splitting this fraction into this plus that and splitting the integrals everywhere. Now, I like what you were suggesting. This is the same as the integral of, now let's see, this would be x to the 2 halves, so that's x, right, over x to the 1 half dx. This is just algebra here. And this would be, we can go on and rewrite that if we want to. What would this be? And you already said it. 2 halves minus 1 half is x to the 1 half dx. And what was that second integral? Rewritten. Oops. Yeah. I didn't write that integral very well. 1 over square root of x, what would that be? X to the what? Negative 1 half dx. Okay. Now let's use our power rule. What would that be? 3 over 2 times 2 over 3. Perfect. Don't mess with it. Yeah, plus x to the positive 1 half times 2. One more little thing. Plus c. Got it. Okay, and this, you can write it. That, to me, is perfectly fine. I think the book likes to write it as 2/3 x to the 3 halves plus 2 x to the 1 half plus c. You could go back and write it in radical forms. I don't see why. This is easy to check. 3 halves times 2/3 is 1 times x to the 1 half. That's exactly what you wound up with there. And this is 1 half times 2 is 1 times x to the 1 half minus 1 half. And that's what you got there. Root of c is 0. Now, that doesn't reproduce that, but you could carry it on through and get the same thing. All right, let's see how the book did. Oh, goodness, how did they write their answers? Why would they do that? Okay? To me, this is fine. Here's how they write it. Yuck. I can't believe they did this. Okay. They wanted to get common denominators. Now, they forget the c for a while here, so let's do that. They put this over 3 and multiply it by 3, right? And they factor out x to the 1 half, which is the square root of x. And they factor out a 1/3. They probably factor out a 2/3, don't they? Yes, they do. They factor out a 2/3 x to the 1 half, which they're calling square root of x. And what is left? The 2/3 is gone. The x comes out of 3, and x to the 1 half comes out of that. That just leaves you x plus 3 plus c. Why in the world would they ever think of doing that? But they did. All right, that ends it for today. I'll give you a few homework exercises so you can listen to your YouTube videos to get them. We made good progress on 4.1. You can do number 5. It should be at Calc Chat. Either 7 or 9, they're both at Calc Chat. 7's at Calc View. Either 11 or 13, both at Calc Chat. 13's at Calc View. Any of the odds 15 to 19, no, 15 to 20, 35. Yeah, I think you can do all those. They are all at Calc Chat. 15's at Calc View. And I don't think we've talked about particular solutions yet, so stop at 35. Good deal. And we will, I thought I marked this with a pencil, but it didn't mark well. One more. And anyone come in late that did not get test on Chapter 3? Test 3. Everybody got it? Okay, good deal. One more assignment. Have a good spring break. Okay? And what will make it good? Doing plenty of calculus problems. That'll make it an outstanding spring break. Of course, right? Good deal. Have fun.